So I think it's time to start. Welcome to this week's ENLA seminar. This is Jörg Liesen from Berlin. I will be moderating today, and it's my great pleasure to introduce Lek-Heng Lim from the University of Chicago. Lek-Heng obtained his PhD in 2007 at Stanford with advisors Jean Golub and Gunnar Carlsson. And if you're interested, the course of Jean Golub, Advanced Methods in Matrix Computations, Iterative Methods from the spring of 2006, where Lek-Heng was the TA, is still available at the Stanford website. And so you could check out this interesting course. There's the original notes of Jean and I think the exercises that Lek-Heng did and so on. Anyway, so Lek-Heng is widely known in the NLA and beyond the NLA community. Among his honors are he's a fellow of the American Mathematical Society class of 2020. He won the Eilers Hans Schneider Prize in 2019 and the Siam Jim Wilkinson Prize in 2017. And these three distinctions of the AMS, Eilers, and Siam, I would say, exemplify the character of his research. He has published a wide range of exciting results, which are usually characterized by a unique combination of different areas of math and computation. And so some examples of his recent papers or titles of his recent papers include tensors and computations, topology and also tropical geometry of deep neural networks, topology of tensor ranks, Hodge Laplacian on graphs, or numerical algorithms on the affine Grassmannian. And so I think today's talk appears to be of a similar interdisciplinary nature from randomized linear algebra to semi-definite programming, and I'm very much looking forward to it. And as always, if you have questions, you can just place them here in the chat, and then either I will read them or I can also unmute you so you can ask directly. And now, Lek-Heng, please go ahead. We're looking forward to your talk.
Yeah, thank you very much for the very kind introduction and for inviting me to give this seminar. So the thing is, there is going to be some, I guess, unusual buzzwords in my talk, right? It's actually a German word, right? You know, just like you mentioned my work in like regarding Hodge Laplacian and like a tropical geometry. Today we're going to talk about something called the positive Stellanzas. Okay, it's a German word. I probably didn't pronounce it well, but you can correct me later. Yeah. So well, the thing is, I'm going to be talking about a problem that's motivated by randomized linear algebra. It's a problem about matrices, right? In particular, it's a conjecture, and I'm going to show you how that I can use, you know, like a variety of tools in matrices and in non-commutative algebraic geometry to reduce it to a problem that can be answered using semi-definite programming, okay, SDP. And the solution of SDP ultimately would be using numerical linear algebra too. Okay, and we'll get to that. Right? So, so I guess there's something in the chat window. Should I? Yes. So, yeah. So, well, so the thing is, why did I choose the title? Right. So I was looking at the past talks in this online seminar series, and I saw that, you know, the path that I'm going to trace, right, for you today, right, even though most of it is going to take you to some uncharted territory, well, I guess for people in numerical linear algebra, right, but the destination, okay, and the origin of my talk would be familiar topics to most people in this community. So of course, reason being that, you know, these are two topics that have appeared before earlier in this seminar series. Okay, so I'm going to start from Ilse's topic, right? Randomized numerical linear algebra. And I'm going to end with Madeleine's topic, right? Semi-definite programming. Okay, so the main players behind this work are, well, primarily, right, I'm going to talk about work of my student, Zehua Lai. He's a phenomenal student, okay? Very, very bright, right? He won the Chinese equivalent of the Putnam, right? It's called the STL competition, right? So unlike the Putnam, right? Putnam, they have 5 winners, 5 Putnam fellows. In China, there is only 1 gold medal, okay? And he got the gold medal. Towards the end, I'm also going to be talking about work by Chris Dessar, whom I've never met, but you know, whose papers I read, okay? So, well, naturally, I'm going to be focusing on work that I know better, right? And that is, you know, this work by Zehua Lai. So in this, my role in this is more like an advisor, okay? More of a cheerleader, somebody who gives him encouragement. He's sort of responsible for the intellectual accomplishment behind this work. Yeah, so let me begin, right? So as I said, I'm going to begin in randomized numerical linear algebra. So of course, right, it's been a topic that is very popular today, but it's what many of you may not know is that randomized numerical linear algebra has a history that's pretty old, okay? Well, so basically, if you want to deal with extremely large matrices, well, the classical way is to use iterative methods, right? And of course, that's even older. That's Gauss, that's Jordan, right? That's Chebyshev, right? So that's a very, very old numerical linear algebra, right? 1823, if you want to go back to the very first published book where I guess what we call Jacobi or Gauss-Seidel was first invented. But the thing is, the randomized numerical linear algebra is almost as old, okay? Like at least, well, it's been around since at least 1950, the first published paper. And it's by George Forsyth, right? The founder of the Stanford CS department. It's in a paper by him and Leibler, whom I do not know, but according to them, the method, right, using randomized methods in numerical linear algebra, that's even earlier than their paper. So they attributed the algorithm that they described in their paper to von Neumann and Ulam. Okay, so it's something that's at least as old as 1950 and likely predates 1950. Now, so of course, the thing is iterative methods allow you to avoid having to like decompose a matrix, like doing LU or QR, and if you have an extremely large matrix, that is very, very helpful, right? So, and randomized method essentially allows you to having look at like every entry in a matrix, right? So, for instance, I can just look at a couple of rows or a couple of columns or just a couple of entries, right? So, of course, the thing is that if you want to deal with matrices that's so large that you cannot like even store it, right? You cannot, of course, iterative methods, you have to at least be able to multiply a matrix to a vector, right? If you cannot even do that, then randomized method is sort of the way to go. So of course, people have thought of combining both, and that's also not a new idea. That's at least as old as 1962, okay? Randomized iterative methods appeared in a paper by Helton. In 1962, he doesn't call it iterative method. So if you search for randomized iterative method, you won't find it. He calls it successive method. Okay, so by successive method, he really meant iterative methods. So the thing is, it's not as straightforward as simply taking like one of these iterative methods like Jacobi or Gauss-Seidel or CG or MinRes, right? It's Michael's creation, or KMR, and then make it a random algorithm. Okay, now the thing is, the kind of algorithms, randomized iterative algorithms that you're going to be talking about today is somewhat obscure in numerical linear algebra. It's not one of this, it's not a randomization of one of this well-known classical or Krylov iterative method, okay? The method, well, nowadays is known by its the name of its inventor, Kaczmarz, I guess, but it's relatively obscure in our field, in numerical linear algebra. Nonetheless, it's very well known in signal processing and in computer tomography under the name ART, for algebraic reconstruction technique. It's very, very simple, okay? Now, this is what it looks like, okay? The Kaczmarz algorithm, right? It's also old, right? It's 1937, not as old as Gauss-Seidel, but nonetheless, it's been around for quite a while. And so what you do is that if I have an n by n matrix, right, I'm going to denote the row vectors, right, AI, right? The AI are not the column vectors, but the row vectors. So the row vectors, of course, that's a vector of dimension n. And the thing is, I can take inner product with, in fact, my solution vector, right? So whatever x that I'm searching for, I'm trying to solve ax equals b. So I can take inner product of row vectors of A with, approximate solutions to my, approximation to my solution x, okay? But so the thing is, the iteration is just this, okay? Xk plus 1 is xk, right? I'm going to start from some random vector. And then I'm going to take a coefficient, bi minus the inner product of ai and xk, divided by the norm squared of ai, right? Ai is the rows of A. And then the thing is, this is going to be a scale that the scalar I'm going to multiply to my row vector A, AI, and this is how I update my initial vector x0, right? That's going to give me x1. And I'm going to keep doing this, right? I is going to go from, it's going to go over the classical way it's done, right? That's Kaczmarz's original algorithm, is to just go over the rows in a deterministic order, right? From starting from the first row to the second row and so on and so forth. So, so as I said earlier, right, this is not so well known, right? The Kaczmarz algorithm in the numerical linear algebra literature. However, you do find it, right? Maybe not under this name in Youssef Saad's book on iterative methods, okay? It only appeared very, very briefly. And he calls it the forward suite, what do you call it? No, forward SOR suite. And he applied it to the normal equation, right? So essentially, he's using the Kaczmarz method, but he's applying it to the normal equation, okay? And he calls it the forward SOR suite for normal equations. It's essentially Kaczmarz algorithm, but he does it in the way Kaczmarz did, right? Do it a forward sweep, meaning you go over the rows from the first to the end. Okay. Now it turns out that this is not such a great idea. Okay. If you try to do it, if you try to go over the rows, right, in the way it's ordered in a matrix from the first row to the nth row. But so Thomas Stromer and Verschainen, well, they have sort of revived this algorithm in 2009. I guess they came from the signal processing computer tomography community, so they were familiar with this. So what they did was that they essentially randomized this algorithm. So it's a very simple randomization. What they do is that they just choose the rows randomly, okay? Now, in order to prove something, right, you have to sort of say what the distribution is. And of course, a simple distribution is to just pick the rows with probability proportional to the norm, okay? So if the norm is bigger, then the chances of you picking that row is higher, okay? So the thing is, even this is not new, okay? So people in computer tomography sort of realize that if you pick the rows in a random order, you get better results, okay? What they did, what Stromer and Verschainen did, was to actually prove this rigorously. And of course, you have to put a distribution on the rows, and this is the probability distribution they pick, okay? So essentially, it's known, right, from empirical evidence that if you randomly shuffle the rows in your Kaczmarz algorithm, then you improve convergence rates dramatically. How dramatically? It's better than CG, okay? If I give you a positive definite matrix, and if you do Kaczmarz, it's better than CG if you shuffle the rows randomly, okay? Now, the thing is, it's, of course, this is a little bit, it's somewhat strange, right? Like, because we expect like convergence, let's say like Krylov subspace methods, right? We expect the convergence rate to depend on the condition. Now, the condition number of a matrix is independent of the way you order the row, right? Any permutation of the rows of a matrix doesn't change the condition number, okay? So this is a bit strange because it's like, you know, what for Kaczmarz, you know, randomly shuffling the row actually improves the convergence rate. What this was actually proved rigorously by Stromer and Verschainen in their paper that sort of revived this method, and now it's very, very popular. I'll tell you the reason. Now, so what they show is that, you know, because this is randomized, so you cannot just talk about how fast the error goes to zero. You have to talk about the expected error, okay? Now, expected error essentially converges to zero linearly, okay? Well, the thing is, linear convergence in our community is called exponential convergence in the machine learning community. Okay, so in a paper, they said exponential convergence, but what they really mean is what we would usually, is what we mean by linear convergence, okay? So the thing is, so this is actually the first time they are able to relate the Kaczmarz method with the condition number of the matrix. Okay, it's also a weird condition number. It's not the usual condition number you expect. It's not a condition number measured with respect to the Frobenius norm or the 2 norm, but you know what's called the scale condition number. Okay, this one here. It's the Frobenius norm on A and the spectral norm, the 2 norm on A inverse. Well, this actually appeared. You know, I'm surprised to actually learn that it appeared in a paper by Jim Damo in his PhD thesis. In fact, right. It's called a scale condition number. Okay, it's frankly, you know, I've never encountered it before, you know, in my life until I studied this paper by Stromer and Verschainen. Okay, so the thing is, and actually a consequence of this is what I said earlier. The convergence rate also doesn't depend on the number of equations. Okay, so if m is greater or equals to n, right? That's, you have more equations than variables, right? It's you have an overdetermined system. No matter how big n is, no matter how many equations you have, the convergence rate is the same. Okay, and it's also sort of borne out by empirical experiments. Now, so
maybe I can just quickly jump in. There was a question of Daniel Schelt. He just asked, what would be the norm of the error here? 2 norm or?
Yeah, there's 2 norms. Sorry. You know, all the norms. If I don't put the for vector norms, right? It will always be the 2 norm. Yeah. So okay. And matrix norm, later on I will tell you what norm it is. Okay. You know, I was a little bit lazy in putting the subscript. Now, so the thing is, why is Kaczmarz's algorithm so popular today? Right? Well, one reason is that it's sort of the base case of a very, very important algorithm, the stochastic gradient descent algorithm, that is essentially, right, the workhorse of modern machine learning, the same way SPD is the workhorse of numerical linear algebra. Okay. Now, so the thing is, and of course, machine learning is very important, right? I just heard this talk by Don Knuth, who says that, well, you know, it's at some point, you know, computer science would probably just go out of existence and be replaced by machine learning. Okay, it's not so long ago. It's just 2 months ago. Now, so anyway, if you apply, well, so what is stochastic gradient descent? Essentially applies to an objective function that can be decomposed into an additive sums of component function, this fi. Okay, so it applies more generally to functions like this. Now, a very basic case, well, in optimization, you don't typically care about higher order terms, right? So, right, you approximate any function you have by its quadratic expansion, the second order Taylor expansion, right? You take the gradient, take the Gaussian, and you forget about higher order terms. So essentially, you can view it as applying to a function like this, okay? A sum of quadratics. And if the sum of quadratics, yes?
Okay, Leaf also had a question. Maybe I unmuted you already. Maybe we can just go ahead.
Yes. What if A is the 5-point discrete Laplacian? What does this look like as an operation on the grid?
The matrix A.
Yeah.
Yeah. So the thing is that if you have a nice a nice operator like this. Okay, if A comes from PDE, when you have a discretization of a differential operator, then chances are that it wouldn't work as well, right? So I'm talking about matrices that comes from sort of data. So A is usually going to be dense. It has no nice structures like what we are traditionally used to in numerical linear algebra. Okay, so what I said earlier, well, I guess I should have this caveat, right? That when I said it outperforms conjugate gradient, I'm assuming that this matrix A has no like special structures. If you have special structures, then presumably that doesn't work. So when they do this kind of experiments, it's like with random A's. Okay. Yeah.
Thanks.
Yeah, you're welcome. Yeah. So anyway, right? If n is equals to 1, right? If I just have a single term, and if A is positive definite, right? Then stochastic gradient descent applied to a function like this, a quadratic function, is actually randomized Kaczmarz. Okay. So randomized Kaczmarz is actually the base case of SGD. If I want to understand SGD, I should at least understand randomized Kaczmarz. And because SGD is so important, and that's because, of course, machine learning is important, everyone is rushing to understand randomized Kaczmarz. Well, at least for the last couple of years. Now, the thing is, the conjecture I'm going to be talking about today is motivated exactly by this thing. Okay. Now remember that what I said earlier, right? I highlighted this word sample, right? Well, so the thing is, of course, I was waving my hand. What do you mean by sample, right? There are two types of sampling strategy. Okay. Two basic types of sampling strategy. It can get more complicated, of course, right? Now, one is that you can sample with replacement, or you can sample without replacement. Well, the thing is, and this is very, very important. Okay. Why? Because the thing is, if I want to sample with replacement, this is something that's not so easy to implement. Okay. If you think about it, it's not really so easy to implement in your algorithms. Okay. In under general scenario. Okay. However, it's much easier to analyze. Okay. If you assume that the rows of that matrix is sample with replacement, or more generally, right? If you have some randomized algorithm, you sample replacement, that means every iteration is now independent. Okay, the randomness from one iteration to the next is independent, right? Every time it's like you draw, a ball from an urn, and then you replace that ball. So it's like every time it's the same. The urn has the same composition. Now, so this means it's easy to prove results, okay? And in fact, the results I mentioned earlier, right, the Stromer-Verschainen results, those are proved under the assumption that, there's you sample with replacement, okay? Now, however, if you sample without replacement, that's much easier to implement, and there's a lot of empirical evidence that is actually better, okay? So what does it mean to sample without replacement? That's exactly what I said earlier. You just randomly shuffle. Right, in a context of Kaczmarz, that you just randomly shuffle the rows, right, of your matrix. Every time I go over I do my forward sweep, I randomly commute the rows of my matrix first before I do that. Okay, so every time it's a different order. Now there's evidence that leads to faster algorithm, not less in the Kaczmarz algorithm. So that's empirical evidence, and it's not just limited to Kaczmarz algorithm. It's actually, you see this in SGD too. Okay, all these papers that I'm citing appeared in the two top machine learning conference, NIMS and ICML. Okay, and there's also some theoretical evidence that can prove under certain assumptions that with sampling without replacement is a better way to do things. Okay, it's faster, you get more accurate results. So let's try to do this. Okay, let's try to actually decide whether it's better to sample with replacement or without replacement. Okay, now the thing is, this might seem like a trivial thing, but it's actually sort of one of these main questions that a lot of people in machine learning were trying to justify. Okay, maybe not a lot, but a significant number of people were trying to work on this problem, whether it's better to sample with or without replacement. Okay, now for randomized Kaczmarz, okay, let me remind you, this is the iteration. Now, so the thing is, even though it's randomized, but the way we analyze the error is exactly how we would do it in classical iterative methods. You know, this is how we do it in, well, you know, in gradient descent, you know, in SOR and in Krylov subspace methods. Right? What you do is that you look at the error. Okay, now error is xk minus x. What is x? X is the exact solution. Ax equals b. Okay, now using that, right, you can get rid of terms in the iteration, and you just get a very nice relation that relates the error from one step to the next. Okay, so the error at step k is related to the error at step k plus 1 by a projection. Okay, it's I minus 8, the row that you sample, right? Projection onto the orthogonal complement of that row. Okay, so this is what I wrote here in my slide, right? So if I sample AIK, that's the row, then I'm going to look at the error from one step to the next is exactly, right, the PAIK, right, the projection onto the orthogonal complement of that row, essentially, right, of EK, right? Now, the thing is, the only thing that we have to understand, so sort of I have to keep in mind now is that, well, this is, of course, an orthogonal projector. It has a whole bunch of properties, right? You know, it's a symmetric matrix, right? It's idempotent, but the only thing that we have to bear in mind now is that it's a symmetric positive semidefinite matrix. Okay, that's the only thing that's going to go into the conjecture. Okay, an orthogonal projector is symmetric positive semidefinite. Okay, so the thing is that if I do this, right, then of course remember this rows AIK, right? The index is random. Okay, so these rows are chosen randomly. So I have to look at, if I want to talk about error, I have to talk about expected error. So I have to look at expectation of the norm, right? So the norm here is the spectral norm. Okay, this is going to be an upper bound, right? It's exactly what we'll do if we do Jacobi or Gauss-Seidel or Richardson or Chebyshev, right? We look at the spectral norm. Okay. Now, in this case, the only difference is that we put an expectation in front. Now, of course, this expectation is well, depends on the distribution, right? So whether you sample with or without replacement makes a huge difference to the value, right? So for instance, if I have k equals 2, I have 2 steps, right? After 2 steps of my algorithm, my Kaczmarz algorithm, if I sample with replacement, right, the expectation is going to be given by the quantity on top. Essentially, it's going to be sum over norms of all the pairwise product, right, where you don't replace, right? This is because you where you do with replacement, right? So AI can be chosen twice. The same row can be chosen twice, right? So that you get terms like this. But if you do it without replacement, then if I select the row A1, then I will never select it again. So if I selected A1, then the next row will be A2, right? So you only have 2 terms instead of 4. Okay. Now, so the thing is, in this case, well, it's quite obvious that, you know, the right, if I have this 2 terms, right, then this is already bigger than the sum of these 2, right? But the coefficient is different. But anyway, this implies, right, that well, this inequality here implies that sampling with replacement has expected error that's bigger than sampling without replacement. So of course you want error to be smaller. So without replacement is indeed better, right, as you expect. Now, so of course, this is not just limited to Kaczmarz. If it's just limited Kaczmarz, people wouldn't be so interested. So this applies more generally to SGD. Okay, SGD, as I said, right, you know, a canonical example, sort of of course, the Kaczmarz case is the base case, right, the simplest case. But this is sort of a pretty good caricature of what goes on in reality, because if I want to optimize a function, typically I replace it with its second order term, right, the Hessian term. Okay, so this sum of quadratics is a pretty good way to capture what goes on in more complicated scenario. Now, if you look at this, SGD gives you SGD essentially the simple way, right? Take the gradient of the I summon, right? The function that's the I summon, right? So this is why it's stochastic gradient descent, right? That summon is chosen with some probability. Okay, it's FIK. This index is random. Okay. Now this eta k here. This is called the learning rate, right? Let's not bother with that. Anyway, it goes to 0. So ultimately, you get exactly the same expression, okay, as before, except that here we have projectors, okay. But as remember, the only thing we care about here is that this is a positive semi-definite matrix. So if you do SGD, this is also going to be a positive semi-definite matrix, right? Because the learning rate is going to go to 0. So, and this is going to be essentially expectation of norm, spectral norm of a product of positive semi-definite matrix. Now, again, the expectation depends on whether you do with replacement or without replacement. Now, what Ben Recht and Chris Ray, what they realize is that ultimately what it boils down to is this inequality. It's a very neat inequality if you think about it. Okay, I'll tell you why it's neat. So it says that if I choose any, if I start with any n symmetric positive definite matrices, right? So this could be orthogonal projectors, it could be identity minus learning rate times AI, right? Just like in a SGD case. Then this symmetric positive definite matrices, if I sum over them with sum over m copies, right? And I sum over the only distinct m copies, right? Then the thing is this inequality is true. Okay, if I look at the spectral norm, okay, on one side, I have to put 1 over n to the m, right? The other side is n minus n factorial divided by n factorial. That's the number of permutations. But so if this inequality is true, the bottom line is that if this inequality is true, then without replacement always beats replacement. So there's a hope that we will never need to worry about which sampling strategy is better, because we can always show that without replacement beats with replacement if this inequality is true. Now, of course, the thing is, let you know that it's actually false. Okay, this inequality is not true. It's true under many scenarios, but it's false. Okay, and my talk today is to tell you how we arrive at that answer. Okay, how we manage to show it's false. Right. Let me first of all point out one thing. Okay, it's not so easy to check this with randomly generated or concocted symmetric positive definite matrices. Okay, one thing is that the 3 numbers that can all be unbounded. The number of matrices can be unbounded, right? The number of matrices begin from, that's n, right? And m, right? How many copies you choose, right? That can be unbounded. That's bounded by n, but as n goes to infinity, m can also go to infinity. The size of the matrix is a p by p matrix that can also be unbounded. Okay. Now, so the thing is, it's very hard for you to generate random numerical experiments to check this inequality, and people have tried. Okay, there's been a lot, it's extensive. This problem was open for 8-9 years. Okay, until it was finally shown to be false. So people have tried over the years to show that it's false. Okay, and the thing is, there's a lot of evidence that it's true. Okay, so for instance, why is it called? Well, by the way, this inequality, right? I call it the Recht-Re inequality. It's they call it the non-commutative arithmetic mean geometric mean inequality. The reason is that it's actually a special case of you can derive the AMGM inequality from it. Okay, I can actually derive something that's even more general, something called Maclaurin's inequality, right? After the Maclaurin expansion guy. Okay, now if I define this sum, okay, this commuted sum, then you can show that if I take m fruit of this sum Sm, then you must get a descending series of inequalities. Okay. Now, so if I just look at the first S1 and the last, then, and if all these numbers, all these are just numbers, then I get arithmetic mean geometric mean inequality. But if I look at anything before the last term, right, S1 is bigger than the nth root of Sm, then I get the Recht-Re conjecture, this conjecture here, for the special case P equals 1, okay, when all these are just numbers. Okay, so at least for numbers, they are true. Okay, for one by one matrices, positive semi-definite matrices. So for non-negative numbers, this is true. Okay, so this is very nice. Now we can also establish this in some small example, right? The most straightforward one is n equals 2. I have exactly 2 matrices and I choose two matrices. Okay. Now the thing is, this it's not entirely trivial. It follows from the result that you can find this paper by Bhatia Kitane. But this was actually discovered by Recht-Re. Okay. So this weird curly way of writing the less than or equal sign is the Loeffner order. Okay. So A is greater or equals to B if and only if A minus B is positive semi-definite. Okay, this defines a partial order on the space of symmetric matrices. Okay. Now, so this Loeffner inequality is correct. Okay. And from this, you can actually deduce that the norm of AB plus BA is always bounded above by A squared plus B squared. Actually, we saw this earlier too. Okay. But it's not hard to prove this inequality. And because of that, you know, the conjecture inequality, the Recht-Re inequality, is true when n equals 2. Okay, you can deduce this from that. And in fact, this special case, the simple case is true under many other scenarios. Okay, I can replace the spectral norm by any unitarily invariant norm. I don't have to talk about positive definite matrices. It's true for any Hermitian or symmetric matrices. And you can even generalize this to infinite dimensions. Okay, but anyway, right, this gives us a hint that, you know, it's easier to look at inequalities like this, okay, than to look at inequalities between the norms. Okay, it's easier to look at inequalities between the matrices themselves, but I have to talk about inequality in the sense of Loeffner order than to look at this. And this is the approach that we will take. Okay, now, so the thing is, there are other cases, right? Once we make this observation, you can prove other cases. Okay, this is a observation by T. Zhang, right, in Florida. So what he showed is exactly the statement I told you earlier. He showed that this conjecture inequality involving norms can be written as a inequality involving the Loeffner order. Okay, so if same thing, right? I have n symmetric positive semi-definite matrices. Now I can always sort of normalize it, scale them so that they satisfy this inequality, right? So if I sum them, right, they're going to be less than or equals to n times the identity, but less than or equals in the Loeffner sense. Then once I make this normalization, right, then for any m less than or equals to n, this is the analog of the Recht-Re conjecture, or not analog, the equivalent of that. Okay. Okay. So it says that if I take distinct sums of m copies of A1 through AN, then it's bounded above by a constant multiple of the identity and bounded below by the negative of that same constant. Okay, n factorial over n minus n factorial. Now we can use this, but now that I transform it into this form, I can use this to prove several other cases, right? Just now I had m equals 2, n equals 2. Right now I can have m equals 2 and n can be arbitrary, right? And this was actually also established in the original paper by Recht-Re. Okay, and Zhang also did this using his own method. Now we improve this to a sharper inequality. Okay, the lower bound can be improved. Okay, that's what we show. This lower bound is actually not sharp. It's actually 1/4. Now, actually, this is an important observation. Okay, meaning that this inequality here, even though the upper bound appears to be correct, the lower bound can actually appear with a different constant. And this is, and for every number, you know, this constant can change. Okay, and this is in fact how we disprove it. What we ultimately show is that this number here, for some bigger m and n, will ultimately exceed this conjectured number. Okay, and I'll tell you how we did it. Okay, now so the thing is, m equals 2, n equals 3 is already pretty hard. Okay, in Zhang's paper, he only did it for n equals a multiple of 3. Okay, now sorry, this should be m equals 3. Sorry, this number should be 3. This should be 3. Okay, and for arbitrary n, it was actually we established that in our paper, right? It's correct. Okay, so this conjecture is correct for n equals for arbitrary n, right? M equals 2 and n equals 3. Those you can be proven. Okay, so it looks like it's going to be correct, right? But it turns out that it's false, right? Once you go up to higher number, it's false, right? That's why it's so difficult to find this. And the trick that I use, okay, the technique that I use is actually the main technique of my talk. Okay, so and the thing is, I guess maybe I spent a little bit too much time on that. So what I'm going to do is I'm going to talk about multivariate matrix functions. Okay, now the thing is, well, of course, you study a lot of univariate matrix functions, the exponential function, right? Some favorite topic of mine, and Cliff has written a magnificent paper on that. So that's univariate matrix functions, right? Now the thing is, unlike univariate matrix functions, multivariate matrix functions require you to consider non-commuting variables. Okay, now that's the only thing that you have to bear in mind, right? If I have to look at multivariate matrix functions, I have to consider functions that was defined by formulas where the variables do not commute. Okay, so I'm going to let capital X1 to Xn be non-commuting variables. Now the thing is, if I do that, then this quantity that I'm interested in, okay, this quantity that I'm interested in, this is actually a polynomial, right? This is a multivariate polynomial in matrices. Okay. Now the thing is, what I'm doing here is I'm just evaluating them on this matrices. Okay. Just like you evaluate univariate matrix functions on a single matrix, you can evaluate multivariate matrix functions on multiple matrices, except that those functions must have non-commuting variables. Okay, so and this is a polynomial, meaning it has finite many terms, it doesn't go to infinity, right? So it's a polynomial. Okay, it's a non-commutative polynomial. Then of course the definition is pretty clear, right? It's a linear combination of non-commutative monomials. And I'm going to use this sort of a symbol that comes from algebra. Instead of using square brackets, you use angle brackets, and this means non-commutative polynomials. Okay, and this little d here means that I'm just looking at the ones with degree less than or equals to d. Okay, now this space has very high dimension. Okay, even for a small number of variables, for a small d, but it has dimension that is essentially given by geometric series. Okay, so the thing is luckily we found an example as soon as m equals 5. Okay, otherwise it would be impossible, right? This number will blow up very quickly. Now, so you can define transpose on monomials, right? Right, because the variables are non-commuting, so you can assume that they are matrices. So you can define transpose. Just like if I take the transpose of product of matrices, I flip the order. Well, it's the same thing, right? For non-commuting variables, they behave like matrices. If I take a transpose, I just flip the order. Now, if I can do it for a single monomial, I can extend it linearly to the space of all polynomials. Okay, so I can define the transpose of any polynomial by simply transposing every monomial that appear in the summand. Okay, and just like what we call a matrix that has A transpose equals A, the polynomial with F transpose equals F is called symmetric polynomial. Okay, now the thing is, why is this important, right? If I have symmetric matrices, that's the case we're interested in, and I evaluate them on a non-commutative polynomial, right? I evaluate F on A1 to AN. In general, this will not be symmetric, right? Because like product of symmetric matrices may not be symmetric. However, if F is a symmetric polynomial and all the matrices are symmetric matrices, then the result is a symmetric matrix. Okay. Now, so the thing is, now that I've done this, I can talk about linear inequalities. Okay, I can talk about LP, right, over the space of matrices. Okay, I can talk about linear programming over the space of, and I can define linear inequalities. Okay, what is a linear inequality? Linear inequality is simply an inequality defined by linear polynomials. So these are polynomial, non-commutative polynomials of degree 1, but because it's degree 1, it's really just a linear polynomial. Okay. Now I can plug in this, right? So each one of these will be just a linear combination of matrices and say that it must be positive in the sense of Lerner. Okay, that this L1 evaluated at A1 to AN, this gives me a positive semi-definite matrix. Now using inequalities like this, I can define sort of polytopes, right? Polytopes are sets of Rn cut out by linear inequalities. Now I'm looking at sets in symmetric matrices, okay, cut out by linear inequalities, right? And so I can say that this set ABL, this is essentially the analog of a polytope in a space of symmetric matrices. I say it's bounded if all the matrices in it are bounded, right, in some norm, right, any norm, right, all norms are equivalent, right? Now, so I can also define a set that I call the non-commutative sum of squares. Okay, now it's going to be clear in a minute why I call it a sum of squares. Okay, this is simply right taking a sum of non-commutative polynomials of the form f transpose LF. Okay, f is any non-commutative polynomial, any non-commutative polynomial. L is a linear polynomial. Okay, so f transpose LF is very similar to what you are thinking of, right? In the matrix case. Okay, now this set is called a sum of squares because a term like this, f transpose LF, is a square. Okay, it's the equivalent of a square in the space of non-commutative polynomials. Okay, now now I'm going to use a deep result. Okay, and this is where I use the German word that I mentioned at the beginning, the non-commutative Positivstellanzas. Okay, it's not positive Nustellanza, it's Positivstellanzas. It's very hard to pronounce, a mouthful. I sort of read it out loud to myself 10 times before I started my talk. Otherwise, I wouldn't even be able to pronounce it. Okay, so what it says is that if I have any polynomial, any symmetric polynomial, right, satisfying some condition, that is always non-negative on a polytope, on this linear BL, right? Remember that BL is a set that is equivalent, right, to a polytope in the usual space, right, but in a space of symmetric matrices. So if this is true, then this means that P has to be a non-commutative sum of squares. Okay, this result is not true for commutative polynomials. For usual polynomials, the result is not true. It's much more complicated. Okay, so this is amazing. This is due to Bill Houghton, right, and has a variety of applications in control theory. Okay, now so to avoid clutter, I'm going to use this this symbol to denote my sums, right, over distinct terms. Now, so I can rewrite Recht-Re conjecture in the form of optimization over polynomial. Okay, this polynomial, right, sum over distinct monomials, right, monomials with distinct terms. So I'm going to find the smallest lambda and the biggest lambda, so that lambda minus that is going to be a sum of squares. Okay, now the thing is, you wouldn't be able to get it right away. Okay, but it's equivalent to this inequality that I'm trying to prove here with this linear constraints. Okay, right, these are now my linear polynomials, right? These are my constraints, and the conjecture is equivalent to lambda 1 and lambda 2 being bounded by n factorial divided by n minus m factorial. Okay, so I guess I'm slowly running out of time, so I better finish up. Now, so the thing is that ultimately, we do not want to use non-commutative polynomials, right? We don't have softwares that work with non-commutative polynomials. We have plenty of great softwares that work with matrices. So we're going to convert non-commutative polynomials to matrices. And fortunately, there's a way to do it, okay? That's because a non-commutative sum of squares, right, like of this form, can be written as a trace of a term like this, right? This beta here is the set of all monomials with a positive definite matrix. Remember that any matrix that can be written in this form is a positive semi-definite matrix, okay? Bottom line is that I can translate the condition that I have to check, whether something I can translate quantities like this, okay? Non-commutative sum of squares into positive semi-definite matrices. Why is that good? Because I know how to deal with positive semi-definite matrices. I have, tons of software that's developed in numerical linear algebra that allows me to do that. So, and I can translate that problem that I stated earlier in terms of non-commutative polynomials into SDPs, okay, semi-definite programming. This may look a little bit strange, right? It doesn't look like a usual SDP, but it is, trust me, this is an SDP. Okay, this xi, these are the non-commutative variables. This define linear constraints, okay? These xi are not variables, they are just placeholders, okay? The variables in your SDP are lambda and yi. Yi are positive semi-definite matrices, okay? So this is just a way for me to write down linear equalities. Okay, it's just a placeholder for the coefficient. Let me skip this. So anyway, let's take an example, right? If I have m equals n equals 5, okay, 5 matrices, and I'm going to choose five of them with replacement and without replacement. So to decide the inequality, I can translate that into an SDP in a standard form, okay? None of this is obvious, right? You have to sort of do it. But so yeah. So anyway, this is now a standard SDP. How do you solve SDP? Right. Well, essentially, it's numerical linear algebra. Okay, solving SDP using the state-of-the-art technique is primal dual and zero point methods. What is that? That is just applying Newton method to the KKT conditions. Okay, and what is that? You do Newton method. Every step you have to solve a linear system. Okay. Now the thing is, these linear systems are not easy to solve. Okay, essentially you have to throw everything in the linear algebra, numerical linear algebra toolbox at it. Okay, Kolaski, Lanchor's, BiCG step, QMR, LDLT, and you have to use every trick that you know, right? Exploit low rank structures, sparsity, in order to solve systems like this reliably in the case of SDP. Okay, I can do this for LP quite easily, but for SDP it's very hard. Okay, now and the thing is, thanks to the availability of SDP solvers, which are built on like the magnificent tools developed in numerical linear algebra, I can get solutions to the SDP that I wrote down before. Now, so this number here tells you that Recht-Re conjecture is false. Okay, this number here, this is a sort of a computer-assisted proof, right? So we use numerical linear algebra ultimately to deduce that this conjecture, right, that we made about a problem in numerical linear algebra or randomized numerical linear algebra is in fact false. Okay, because this number is bigger than 120, right? When m and n equals 5, 120 is the conjectured lower bound, but it's in fact 144. Okay, there's other ways to check this. Okay, we are very sure it's you can check that it's correct. Now, and what about counterexamples? Okay, so the thing is, as I said, it's not so easy to create actual counterexamples. But now that we know where to look, okay, just now we didn't know what value would he give us a counterexample. Now we know that there is definitely going to be a counterexample for n equals 5, n equals 5. Well, and the thing is, there are people who actually do it. Okay, based on our formulation, we know that the sum of 5 matrices, what n equals 5, there must be 5 matrices, must be bounded above by 5 times identity. And so that's where the work of Chris Tassar comes in. So a few months after we came out with our paper, we published our paper, he came out with the example. It's very simple, right? It's in fact a rank 2 perturbation of the identity, right? And it satisfies exactly this condition, okay? But if you plug that into our polynomial, right, the polynomial that I gave you earlier, it has eigenvalues negative 142, very close to what we have. Okay, then that's less than negative 120. Okay, so which means that this conjecture is false, and you have an explicit checkable counterexample. Of course, you still need to use softwares to check this, even though it's a 5 by 5 matrix. But in principle, if you don't trust softwares, you can still do this by hand. Okay. So thank you very much. That's my talk. Well, I'd like to thank the organizers for inviting me. And the part about SDP softwares, I had a lot of discussion with Kim Chuan-To, who's one of the creators of SDP3, and that is very much, I'm very grateful for that. Thank you.
Thank you very much. That was a fantastic talk on which used quite a few deep results, including this non-commutative Positivstellensatz. And also, I have to say this SDP3, that is really an amazing toolbox that I really enjoyed to use. There were some questions, so I will just unmute Michael Saunders so you can ask your question yourself. So, can you go? Yeah. Go ahead, Michael.
Lek-Heng, in one of your early slides, you had a sum of terms, a sum of n terms. I presume n was different from the dimension
yes.
of the.
Yeah, so I switched my. So the thing is, it's sort of impossible to have a unique. Well, initially, my matrices are m by n, right? After a while, right, as soon as I talk about Recht-Re conjecture, right, the n becomes the number of matrices, m becomes the number of copies I'm going to choose. Okay, yeah. So initially, m and n was, of course, my dimension of a matrix when I was talking about Kaczmarz. Okay, but I sort of forgot to mention that.
They were the same for a while, you mean?
So anywhere after this part, okay, right? So yeah, right here, well, of course, initially what I said was that, oh, sorry, yeah, okay, sorry, yeah. Initially, what I said was that here M and N, you're talking about this, right? M and N are my dimensions of my matrix. Okay, so the thing is, after this part, the meaning of M and N has changed. Okay, after this second section, the meaning of M and N means how many copies I'm going to choose. Okay, and from here onwards, essentially, is consistent. I have N matrices, right? All P by P, also definite. And for any M less than this,
simplest slide though, I forget which one. Just a simple sum.
This?
No, simpler yet. Sorry.
So what was it about, SDP, or was it about
It's just a
SPD?
simple sum of n terms, but it seemed unlikely that n was the dimension of the variable.
Oh yeah. I guess even on in my beginning part, I have, you're talking about this, right? This n. Yeah. Again, this is I shouldn't have used the same n. Okay, like yeah. Okay, so it's a.
There's another one yet, but yeah, that's the idea.
Yeah. So there was some. I didn't keep my notation sort of invariant from one part of my talk to the other. Apologies for
don't worry. Okay.
Okay. Thank you, Michael. There was one question on YouTube, and I think, let me see, it was by Riley John Murray, and there's also, I think, the same question by Hiroshi Murakami. So I will just read the YouTube question. Also related to the beginning of the talk, when it comes to the convergence rates of CG versus Kaczmarz, doesn't CG use the standard condition number? And here you had this other Demel condition number with the Frobenius norm. Isn't the standard condition number far smaller than the other one?
Yeah, this is obviously because of the when you have this is a slide, right? The Frobenius norm is always bounded above by the two norm is bounded above by square root. Frobenius norm is bounded by square root n two norm, right? So because of that, it's because of that, you can sort of lower bound and upper bound is in terms of the usual condition number. So it's but the thing is, for some reason, this quantity is the relevant quantity you look at in this scenario. Yeah, it's called a scale condition number, apparently, by Demo in his his thesis.
Okay, good, thank you. Yes, so I guess everybody can unmute themselves. If you have further questions, you can just unmute and speak up directly. And if there's nothing, then I think we're right on time. And I thank you very much again for your talk.